Hello everyone, and I hope you all had a very happy new year. It's getting a bit cold here actually, which is a little bit strange for Texas in general. But anyways, I was scrolling through the Stack Exchange the other day, and I came across a fun little problem that led me into the depths of a Wikipedia article, where I found this right here, and I thought it'd be fun to evaluate. So here we are. We have the sum from n equals 1 to infinity of z to the n times the nth harmonic order of order m. So let's get evaluating, shall we? This term right here, so this right here, as I just said, is the nth harmonic number of order m. And what I mean by that is you can think of that as almost like a partial sum of the zeta function. So this right here is the sum from k equals 1 all the way up to n of 1 over k to the m. For m greater than 1, in the limit as n goes to infinity, this is just going to approach the same value as the zeta function. But let's get evaluating, shall we? Let's just combine all of these into one big sum. So we're going to have the sum from n equals 1 to infinity of the sum from k equals 1 to n. And inside we have z to the n over k to the m. And the way we're going to evaluate this is actually a little bit fun. What we're going to do is split this up into two sums now. We're going to take this right here and split this up into the sum from k equals 1 to n minus 1 of z to the n over k to the m. And then plus just the term we just chopped off, right? So we just need to plug in n for m, or sorry, n for k. So we have z to the n over n to the m. And this right here is the part that is a bit special. Because this right here, because there's a sum, all this is being summed, remember, from n equals 1 to infinity, this right here is just, by definition, the polylogarithm, which can be expressed as Li sub m of some z right here. And now, separating our terms a bit more, we see that this is equal to, well, the sum from n equals 1 to infinity of the sum from k equals 1 to n minus 1 of z to the n over k to the m, and then plus Li sub m of z, or the mth polylogarithm of z. But an interesting thing also arises right here. Whenever we plug in this sum, n equals 1, we see that we have a sum from k equals 1 to 0. But for all intents and purposes of this video, because we aren't exactly extending this summation for fractional values, and the reason I say that is because you can extend the harmonic numbers right here, for example. You can actually extend those into having fractional values, right? So although it might not make sense to plug in n equals like a half right there, it sort of parallels the extension of the factorial with the gamma function, right? We can plug in a half factorial, even though that traditionally that doesn't necessarily make sense. The same goes here, except you do it not with the gamma function, you do it with the digamma function. But at any rate, here it does not make sense to sum from k equals 1 to 0. So that term is actually just going to be defined as 0. In fact, if you actually plug that into Desmos, the result you get is literally just 0. So what this means is that instead of summing from n equals 1 to infinity, what we're going to be summing from is from n equals 2 to infinity. We can rewrite this now as the sum from n equals 2 to infinity of the sum from k equals 1 to n minus 1 of z to the n over k to the m. But this right here isn't the nicest, right? Ideally, we'd like to maybe get another term where we can factor out another polylogarithm. So let's reindex this sum over n starting at 1. So what we can say now is that this can become the sum from n equals 1 to infinity, our upper bound is not going to change, obviously. The sum from k equals 1 all the way up to n now. But what that means is that the z term is now not z to the n. It's going to be z to the n plus 1. So now we have z to the n plus 1. all divided by k to the m. But this right here we can deal with quite easily, and you'll see that we get effectively the same thing as before. So this right here, right, is the same form of the thing we were originally dealing with right here. The only difference is that we have an additional z out front. So writing the entirety of our results out in terms of this sum right here, we have the sum from n equals 1 to infinity of the sum from k equals 1 all the way up to n of z to the n plus 1, but we can just write this as z to the n over k to the m, then stick the z out front of the sum, and then plus this polylogarithm of this mth polylogarithm of z. And we know that originally this was equal to this right here, this bit right here. So bringing that down, we see that we have the sum from n equals 1 to infinity of the sum from k equals 1 to n of z to the n over k to the m. And you'll see that these terms right here are the exact same. This term here is equal to this term here, only that we have an extra z out front. So what we can do is actually just solve for it, right? So just subtracting both sides by this right here, we see that we have, in factoring of course, we see that we actually have 1 minus z times all the sums is equal to our polylogarithm. Solving for our sum, we can see that we just divide by 1 minus z, and we see that the sum from n equals 1 to infinity of the sum from k equals 1 all the way up to n of z to the n over k to the m is just in fact equal to the mth polylogarithm divided by 1 minus z. And that right there is just a pretty neat result. This is a shorter video than the last couple, which is probably for the best. Making 30-minute videos is quite a lot. But I hope you all enjoyed and are staying warm. Thank you for watching.